Welcome back. I think we finally figured out how to, host the videos and get them online. Good old YouTube. So for anyone who misses a lecture and needs to catch up. Of course, I still hope you'll show up most of the time in person, but the two last lectures should be online now. Just Google, you should be able to search Google or YouTube or something for a YouTube channel called COM-402. So I don't know, I haven't actually tried that search yet, but hopefully it shows up.
So the search works, but I also posted the URL for the channel on Moodle.
Okay, or look on Moodle. Great, thanks. Yeah. Okay, so we're so far so good in terms of that experiment, and so hope it'll be useful to some of you. Okay, so last lecture we talked about a number of threats. We didn't get through quite all of them, all of the classes of threats, for lack of time. I encourage you to go take a quick look through the slides, but since we're on a tight schedule it's not critical to understand all of the details. I'm just going to go right ahead with this lecture's topic, which is Introduction to Basic Concepts in Cryptography that we'll use in the rest of the course. So how many of you have taken a crypto course of some kind? Okay, so I'm afraid this lecture isn't for you, sorry, because this will be very basic, and we'll just be looking at crypto building blocks from a more or less black box perspective, not really getting into the math. That's what a crypto course is for example, Serge Vodinet's a very deep, excellent crypto course. So this is just a super high-level overview, mainly for those who haven't encountered crypto much before, to understand some of the basic concepts and the building blocks and how we'll need to use them in the rest of the course in exercises and use them as tools in information security. Okay, so we'll talk about cryptography in general a little bit, and then specific types of cryptography tools, namely symmetric key cryptography, the data integrity problem, then get into public key crypto, public key infrastructure, and end-to-end encryption and TLS. Okay? So let's first talk about basic goals, right? So crypto is everywhere these days. And I don't just mean cryptocurrency, like increasingly the finance community is using the term crypto to mean cryptocurrency, as opposed to cryptography, which is what it used to mean. But so there's increasingly a little bit of confusion there, but here I mean cryptography, not cryptocurrency. So anyway, that kind of crypto is already everywhere. It's used for all kinds of communication protocols, secure HTTP and Wi-Fi security protocols and stuff like that. It's used at all different levels of systems, like disk level encryption, like Veracrypt or BitLocker operates at the disk level at a very low level, close to the disk drive. It's used in authentication, obviously cryptocurrencies, digital rights management to keep all of us from illegally copying Game of Thrones and stuff like that, right? So what exactly is cryptography? Well, it's basically a toolbox with many different types of mechanisms. There is not just one kind of encryption, one notion of encryption or cryptography. It's a whole toolbox that's quite diverse and constantly growing. And it's used to secure data in many ways and at many levels of the system. Cryptography is not an end-all solution to all security problems. In fact, it's never effective outside the context of a larger system it's used in. And very good crypto is very often used in really bad, completely broken ways in a larger system that renders the crypto completely ineffective. So to reason about the security of any cryptography, you've got to reason about both the security of the cryptographic algorithms themselves and the security of the system and the context they're used in, right? In cryptography, we use these tools to reach a variety of different types of security goals and properties, and these are often orthogonal. Usually we want several of these in combination, but they're orthogonal separate properties. So confidentiality is the most obvious one. Well, kind of the classic use of crypto is for encryption, namely to make something, to keep a secret, keep something private so that only the people with the keys can read it. But then just as important, and often more important in today's world, is integrity, ensuring that data in transit or stored on disk or something hasn't been modified by unauthorized parties. Then there's authentication, ensuring that the source, the origin of some data is who or the system or person you think it's supposed to be. Accountability, namely, if something goes wrong, can you find who's to blame or what system is to blame? Can you trace back what went wrong if something goes wrong? Availability, meaning that means, does the system perform well and stay up when you need it, or does it, kind of go offline and cause all work to come to a halt for long periods of time? Then there are many more specialized services that are often associated with these things, like associating timestamps or associating properties with data that cryptography is often used for. So cryptography goes way back in history. This is kind of a super brief historical look. It goes back to, 50 BC, when the time of Julius Caesar, when the supposedly anyway the Caesar cipher came about. This is basically the simple substitution cipher, where you substitute one letter for another. The simplest way being, all A's become B's, all B's become C's, and so on until all Z's become A's, right? Not a very secure cipher. Pretty easy to figure out, but it kind of at least obfuscates things, and it was a starting point. But then a very important kind of conceptual piece of progress came in 1883 with Kirchhoff's principle, which is that to define cryptographic systems such that to separate the secrecy of the algorithm from the secrecy of the keys, to introduce the notion of keys. And the idea that you should strive to assume that the algorithm is not secret, that anybody can analyze and try to crack the algorithm, and it should hold up to public analysis of the algorithm. And the only real secrecy dependency it should have is the secrecy of the keys. And we'll get to that in a minute. But then 1917, 1918, cryptography, kind of started advancing in practice during the First and Second World Wars. First of all, in the First World War, the use of one-time pads, and then in the Second World War, the Enigma machine, which was a major cryptographic advance, and the cracking of the famous cracking of that by the Bletchley Park project. Alan Turing and his company played a really major role in the war on both sides. And then ever since then, governments around the world have recognized the importance of cryptography in all kinds of forms, and increasingly industry as well, which led to a variety of important standards and developments, such as the data encryption standard, and then the development of public key cryptography, a big advance in the 70s. And then, many continuing advances in terms of specific algorithms and stuff. So, so let's now start back at the basics. I mentioned the Caesar cipher. So one of the most basic substitution ciphers, just take one letter and you know, bump around around the alphabet as a, you know, circular modulo 26 ring by some amount, and this kind of obfuscates, you know, kind of obfuscates text. Now you can look at this as a super simplistic keyed cipher. There is a key here. What is the key in the Caesar cipher? Yeah. Yeah, exactly. The number of letters, you know, it's the value we add, you know, to the letters modulo 26, right? To the number, and so, you know, different keys will produce different encryptions, will, you know, produce different looking ciphertexts. Now, none of them are very secure, of course, but, you know, if we squint and pretend they're, you know, we're onto the right idea anyway, and that's the notion of key, essentially, in Kirchhoff's principle that, you know, I mean, you know, obviously this, you know, the Caesar cipher is not secure, but it does have the notion of key, and Kirchhoff's principle was if you do have a key, you should evaluate the security of, or insecurity of the cipher based on, you know, only on whether on the key being secret, not on the algorithm being secret, right? And so this led to various other advances in cryptography. Now, one of the most fundamental types of ciphers that actually is secure, and it's provably secure on information theoretic assumptions. Now, these information theoretic assumptions often aren't all that realistic by themselves in practice. They're not realistically applicable without major other assumptions or caveats. But taking that, you know, with a grain of salt, if you just use a key that's the same length in number of bits as the piece of information you want to encrypt, and you assume that key is you somehow get that key by flipping random, you know, fair random coins. You have a perfect source of randomness, you know, fair coins or whatever you have, as long as you know, create a key that's the same length as the message you want to encrypt, and, you know, perfectly random, then you just use a simple transformation combination such as XOR or addition modulo something. You know, this can be done in, you know, in the alphabet as well, just like Caesar cipher, where you flip 26-sided, you flip a 26-sided die for, if such a thing exists, for each letter you want to encrypt. And so basically the idea is you have a new random, you know, bit or character or symbol of key material for each bit or piece of information you want to encrypt. That is a one-time pad. And, you know, again, like I said, you can prove this provides perfect secrecy in principle. Well, what's the big practical problem? Well, if you have to, so both the encryptor, both the sender and the receiver of the message have to have that same key material in order to encrypt or decrypt, and, you know, that's big, right? Now, like I said, this was actually used in World War I, and it's still used in some cases where, you know, for example, if you can pre-share a secret, for example, you know, print out a big book full of, you know, random numbers, and this is the kind of thing they did. They, you know, printed pages and pages and pages of random numbers, and you develop a protocol where, you know, if this person here wants to send a message to that person there, and they both have this book of random secrets, they look up the page for this date, or, you know, for the particular day the message is dated or something, and the sender, you know, encrypts using that one-time pad, and the receiver decrypts it. Then, you know, when they receive it using that same page, as long as the key, you know, the page itself is secret and it's used properly, this is perfectly secure, right? And but it requires that inconvenience of pre-sharing those potentially large amounts of key material, right? Now, what's the other downside of one-time pads besides the bulkiness of the key material? And those of you who took crypto courses, this should be trivial, right? So, what can go disastrously wrong with one-time pads if you're not careful? Anyone? Yes?
But it's there. So if we actually use the same...
Oh, yes. Yeah. Okay. Yeah. Exactly. So why... Okay. Yeah. So why... why must keys not be used more than once? What goes wrong?
So if we use it twice, then actually if we XOR the two ciphertexts that were produced by the same with the same key, we will actually receive some information from the messages.
Exactly. Yeah. So if you ever use the same key twice to encrypt two different messages, then the attacker can just take those two ciphertexts, XOR them together. The key just vanishes out of that, because that's what XOR does, and it gives you the XOR of the two plain text messages. And often that is not at all say, by there, then the attacker is totally won. You probably quite a bit of, parts of one message are predictable, or, zeros or spaces, or, stuff like that is typically really easy. Once you've gotten the XOR of two plain texts, it's not hard to basically break the content usually, right? Yeah, so one-time pads have these nice properties, but also really bad properties. And so this led to more sophisticated encryption algorithms in the class of symmetric key cryptography, right? So now, just like in one-time pads, symmetric crypto systems in general, again, assume the sender and the receiver have copies of the same key. They share an identical secret key, and that key can be used to go from encrypt from plain text to ciphertext, and then by the receiver to decrypt, going from ciphertext to plain text. But of course, there are many different ways to do this. So just to go through a few of the examples, first let's look at stream ciphers. So a stream cipher is kind of the more practical equivalent of a one-time pad. It uses a pseudo-random generator, or a keyed expansion, a pseudo-random key expansion function. Basically, the whole idea is that a stream cipher takes a small key that's a small fixed length, like say 128 bits or 256 bits or something, and then expands it into a large pseudo-random stream using this pseudo-random number or a pseudo-random bit generator. A very well-known classic example of this that was used for a long time was RC4. It was used in a lot of systems. It was discovered to be insecure because it wasn't generating truly random, it was discovered that it was pretty easily to distinguish, in some cases, some of the outputs it was producing from statistically random noise, and so it's considered thoroughly broken now and not something you want to use anywhere. But it's actually also an interesting design by Ron Rivest. That's where the R in the letter, the name comes from. And it was used for quite a while. And basically, to use a stream cipher, you have a message of a given length. You put the key into the pseudo-random bit generator and generate as many random bits as you need to cover the message, the same length of the message, and then you combine them, for example, with XOR most commonly to produce the ciphertext. And then on the decrypting side, the receiver does the same thing. It just puts the same key into the pseudo-random generator, generates the number of bits corresponding to the length of the message it receives, and XORs it to decrypt the message, right? So stream ciphers, when they're available, they're nice and simple. to use, and they have this nice property that, again, we've achieved the property of being able to use a small key to encrypt and decrypt a large message, right? So if the stream cipher is a strong stream cipher, it should also be hard to decrypt, but it's important, one of the theoretically, formally important distinctions is we've given up the information theoretic security. So, no stream cipher, stream ciphers in general provide only computational hardness, not information theoretic hardness, in that they tend to have some state where if an attacker could in principle run an exponential time algorithm to reverse engineer the key based on a small part of the ciphertext, then they would have the key and then they could decrypt the whole thing. And so you've lost the perfect information theoretic security of the one-time pad, but and you're dependent on the computational hardness of the stream cipher. And indeed, some of the classic stream ciphers, like I mentioned, have been broken. Although we still do have other stream ciphers that are still believed to be secure, like Salsa 20 or the Cha-Cha stream cipher, right? So another way popular way to build encryption algorithms is by a tool known as block ciphers. So block ciphers are typically a very low-level component piece of cryptographic algorithms that you never use in an application by themselves, at least not if you're sane, but you typically use them as a building block for larger encryption schemes and other applications. So fundamentally what a block cipher does is take a key and take a fixed length set of input bits and encrypt it to produce the same number of output bits, ciphertext bits, or that's running it in the encryption direction. You can also run it in the decryption direction, in which it takes the same key, a fixed n ciphertext bits, and goes backward to produce the original n plaintext bits, right? So the attraction from a cryptographer's perspective of this design is always using the same n bits allows the cryptographer to kind of focus attention on the kind of the internals of the cryptographic algorithm, use very efficient operations that operate on fixed amounts of data, like 32-bit and 64-bit adds, rotates, and stuff like that, and compose a very tight package that only needs to deal with fixed blocks of data and not arbitrary length messages. And so this is kind of a convenient building block, and there's many examples of block ciphers, including one of the earlier very popular widespread data encryption standard, which is now effectively broken just because, mainly because its keys are way too small now. You can more or less just brute force DES with today's technology. It also had other flaws that were gradually discovered as well, but it was never completely broken. But basically the key size is definitely too small. So now, and DES was basically replaced with the advanced encryption standard AES, which is also a block cipher that uses larger blocks, block sizes of 128 bits, and variable key sizes between 128 and 256 bits. And so this is super common, and as a result, it has hardware support in many processors, and so it's very efficient. Now, like I said, block ciphers are never a tool you want to use to encrypt a whole message by themselves. You have to use it in some kind of mode of operation to encrypt or decrypt larger messages. And as an example of a bad way to do this, kind of the naive way to use a block cipher is called electronic codebook, which is to take a big message, however big it is, and break it up into, block sizes worth of plain text and put each plain text through the block cipher with the same key used for, each block of the message and produce a block of ciphertext, right? But you can kind of see what goes wrong if you encrypt something this way. For example, if you encrypt a JPEG image of a Linux penguin that way, the thing on the right is the ECB encrypted output image. Now, why, so is that a secure encryption? Well, obviously not. Something went wrong, right? And what went wrong, as it says, is because the block cipher is deterministic and you're using exactly the same key throughout the whole ciphertext, throughout the whole message, any two blocks that happen to have the same plain text will also have the same ciphertext, right? And so that's what you're seeing in the pattern to the right. A lot of the blocks in the JPEG are, original JPEG are pure white, and those all get, encrypted in exactly the same way to the same output block, and, you can, it clearly leaks quite a bit of information in that kind of scenario, right? So definitely don't use ECB in any real cryptographic scenario. Now, there are many other modes of operation, other ways to use block ciphers that are, much better. And one of the standard ways that is believed to be secure, and I understand has been proven secure under some assumptions and context, is called CBC, or cipher block chaining. And the basic idea here is that, kind of the basic problem in the previous example was that we were encrypting each block the same way, right? So here we're using chaining to, we're chaining the blocks together in a kind of a sequential fashion to make each block depend on the previous block. And we do this to ensure that, the encryption of each block is, depends on everything before it and is different from one block to the next, right? So how does this work? In CBC, we always have to pick an initialization vector, which is usually just a random number. And that has to be typically added to the ciphertext. It has to be either transmitted or known to the receiver in some other way, communicated to the receiver or known to the receiver in some other way. It doesn't really matter what it is, but it has to be unpredictable and it has to be fresh for each new message to make sure that each new even if we send the identical messages twice, we typically want different encryptions. And to achieve that, we have to pick fresh initialization vectors for each message, right? So as long as we do that, we basically start with a random initialization or fresh initialization vector. We XOR that with the plain text before encrypting the first block, and that produces the first block of ciphertext. Then for each subsequent block, the previous ciphertext block acts as a new initialization vector for the next block. Basically, each previous ciphertext block gets XORed into the next block's plaintext before encryption. And we just kind of iterate through the whole way. And because the block cipher is basically acting as a pseudo-randomizer, kind of each of these kind of inputs is pseudo-randomizing the next block. Therefore, that's eventually producing an output that's going to look really random, assuming the block cipher is good, right? Now, this is, like I said, this is a pretty secure standard way of actually using block ciphers. Do you see any downsides to this? Why is this not necessarily the end of the story in the use of block ciphers? Any limitations or problems that might motivate other ways, other modes? Yes?
You cannot parallel process it?
Yeah, great, exactly. So this is by definition and absolutely constrains you to serially processing one block after another. You cannot parallel process, process the encryptions in parallel unless you've broken the encryption algorithm. And if you've broken the encryption algorithm, you shouldn't be doing this in the first place, right? Yeah, so if you want any parallelism, you do not want CBC, but plenty of other modes try to address that by doing slightly more complex things that allow you to parallelize things. One example of a more parallelizable mode is what we call counter mode, and this is essentially a way to use a block cipher to make a block cipher emulate a stream cipher, right? We talked about stream ciphers. They're just pseudo-random numbers. You put a key in, you get as many bits as you want on the output. So what a counter mode, a block cipher in counter mode is basically using the key. So the same key goes in for all of the blocks, but what comes in the top is not, kind of a part of the message, but just a counter. So typically we have a nonce that it often identifies the message or is sometimes just a random number. And then we have a counter that goes from 0, 1, 2, just counts the blocks of the message that we want to encrypt. Each of those goes through the block cipher, comes out, and the output of the block cipher we use as n bits worth of stream cipher output, right? So kind of the result of all of those, block ciphers, collectively, we just concatenate them, and that's our stream cipher output. We use as many bits as we need to XOR with the message. So XOR the plain text with the appropriate bits of the block cipher output to produce the ciphertext, and the receiver just does the same thing. It runs the block cipher only in forward mode. Nobody actually needs the decrypt function of the block cipher in this case. We're just using it as a pseudo-random number generator. And then the receiver just takes, again, the stream cipher output, XORs it with the ciphertext to get back the plain text, right? So this is another simple way to use block ciphers, and it's also quite secure under the right, if used in the right way. Now, based on the issues we talked about with one-time pads and with stream ciphers, what might be a disadvantage of stream ciphers? So we got parallelizability. That's great. So you can see all of those can operate in parallel. We can just shove successive counters into successive blocks in parallel. This is perfectly parallelizable. That's great. What might go wrong if a counter mode cipher is used in the wrong way? Yes. Mm-hmm. Yes.
We can only use the same key, otherwise the attacker can just sort the...
Yeah. So we're back to the key reuse vulnerability of stream ciphers, right? If we ever mistakenly reuse the same key with the same counter and nonce, for two different... you were going to say... Yeah, so if we don't change the counter or nonce for two successive messages and you reuse the same key to encrypt two messages, then we've completely lost security, again, using the trivial XOR attack, right? So
So I just wanted to say,
yes.
That's the purpose of nonce there.
Exactly, yes. So if we are using this correctly, then what we're doing is we're changing the nonce with each message, either incrementing it or picking a new big, sufficiently large random number. If we're using it right, then we won't have this problem, right? So counter modes are perfectly secure as far as we know if you're used right. If they're used right, if they're used wrong, they're disastrously insecure, right? So that's, again, kind of illustrating the importance of reasoning about these in the context of the system. Yeah?
I don't really understand how is it the error propagation here, because it seems like it's not error propagation, but where the previous one was, right?
Yes. That's another very important. So one of the properties of CBC is, suppose an attacker, a message gets modified in transit. We haven't talked about, we'll get to data integrity in a minute. What happens if an attacker flips a bit somewhere in the message in transit, right? So in CBC, flipping a bit of one of the messages will cause all of the remaining blocks to look jumbled, right? This can actually lead to attacks on CBC, but they're not, kind of real obvious. On the other hand, so flipping a bit, maliciously or accidentally flipping a bit really kind of renders the rest of the message normally unintelligible in CBC and makes it really obvious that something went wrong. What happens if an attacker flips a ciphertext bit, as a counter mode encryption goes across the network? Yeah.
So only the block of the plaintext for that ciphertext will be changed, right? And the other ones will be corrected.
Yeah, but even more specifically, only that block is affected, but even more specifically, only that bit within that block, right? So flipping one particular bit in the ciphertext of this one particular block will exactly flip that plaintext message bit when everything comes out the other end. Now, do you see the problem? So suppose the message being sent is a message that's kind of in a standard format. It's a struct that that tells a server that asks a server to do something, and one bit in a known position says, whether to give away all permissions or not, or, whether, or to use the, there was this analogy, the airplane, in the airplane, there's this one bit that says wings stay on or wings fall off, right? And so if the attacker can, the attacker knows where in this struct the wings fall off bit is. He can't see anything, in the message, but he can flip the wings fall off bit, and flip that bit to, the other value and cause disastrous things to happen because, if the message is not integrity protected. Yeah, so the attacker really has, pinpoint ability to muck with the plain text if it's not also properly authenticated. And we'll come back to that, but that's widely seen as a downside to counter mode. If it's used without authentication, it's disastrously insecure in terms of authentication, data integrity. So, okay, so that's kind of a preview of the data integrity part. Let's look more specifically at data integrity, right? So we've been talking about the goal of confidentiality, just keeping information keeping secrets from leaking. But in practice, we're just as worried about, and sometimes even more worried about, integrity, ensuring that the thing that was sent is the thing that was received, and an attacker didn't have the opportunity to maliciously change something. So integrity ensures that data is not modified by unauthorized parties. And all of the symmetric crypto algorithms that we've been talking about so far do not provide good integrity in themselves. Like I mentioned, CBC alone is maybe a little bit less completely broken, or a little bit more robust to integrity attacks than counter mode encryption, but not much. There are really bad things you can do with unauthenticated CBC as well. And so you don't, in practice, ever want to use, a cipher without some kind of additional data integrity mechanism. Yeah, and so here's the point, just made in the case of counter mode or one-time pad ciphers. If you flip a bit in the ciphertext, it just causes that same bit to flip in the message. And so to maintain integrity, we usually use a different class of cryptographic primitives. The most fundamental that's used in all kinds of ways is the cryptographic hash function, right? And so the basic idea of a cryptographic hash is it's kind of the functional opposite or dual of of the stream cipher. A stream cipher takes a small fixed length input, produces an arbitrary length output. A cryptographic hash takes an arbitrary size input, pseudo-randomizes it, and produces a small fixed length output, right? So it's like a hopper. It takes anything arbitrary size in, compresses it down to a small fixed length digest, right? And a well-designed hash function generally has 3 properties that we care about. It should be one way, meaning it's easy to compute, from one input get the corresponding output. It should be very hard to take an output and find an input that hashes to that, right? So what's this property useful for? For example, I mentioned crypto is increasingly getting misused to represent cryptocurrencies, and Bitcoin mining heavily depends on this one-wayness property, right? So what Bitcoin miners are doing all the time, spending more energy than many small countries all the time is just computing hash functions, putting in innumerable inputs, trying to find an output that has a bunch of 0 bits at the beginning of the hash. And that's kind of a winning lottery ticket, a winning block. Now, if it was discovered that the SHA-256 hash function that it's based on does not, after all, have the one-way property, then Bitcoin mining would be instantly broken, right? So a miner could just say, OK, I'm now going to construct an output that has the requisite number of 0 bits on the beginning, and I don't care about the other bits. I'll construct something, and then reverse engineer, go backwards to find a valid, find an input that produces that output. Then I could, I could create any block I want. I've broken Bitcoin as well as the hash function, right? So that's an example of where one-wayness is important. The second property that's a little bit more subtle, though, is collision resistance. So in a good hash function, it should be effectively infeasible to find any 2 inputs, however you find them, that produce the same output. Here we don't care what the output is. We just care about whether we're able to find 2 inputs that produce the same output, right? And that should be hard in a good cryptographic hash function. And then finally, we typically want hash functions to have pseudo-randomness, to be indistinguishable from a random oracle. So if you just hash, say, counters, from 1 to n, the results should pass all of the same randomness tests that truly random coin flips would pass. And there are a bunch of statistical randomness tests, and those are standard parts of the test suites for any good hash function, right? So hash functions are used for all kinds of things. Generally, the most common use is, well, you take some piece of information you want to authenticate or integrity check, and you store the hash of that information next to the information itself, or you communicate it separately. And then if the receiver received the correct hash and the correct information, they can rerun the hash function and check the hash. Hash functions are also used, I mentioned they're used for proof of work. They're used often for storing passwords and other things. Now this is kind of a bad use of hash functions, at least by itself. In password databases, you typically take the password the user entered, and you never store the clear text password, but you hash it first, often adding a random salt to make sure that the same password doesn't always hash to the same thing. and you store the salt and the hash of the password in the database. Now, as we'll see later in this course, this is kind of a bad thing to use cryptographic hash functions for, at least by itself. And it's bad because passwords are often low entropy sources of input, which means they're basically brute force guessable. Right? You know, if you capture a password database, even a hashed password database, and it's 100,000 user accounts, you can be pretty certain that some of those users have picked bad passwords like 1, 2, 3, 4, 5, 6. And then you just go through the database looking for, okay, 1, 2, 3, 4, 5, 6 with this user's salt, does that hash to that hash? You'll probably find one, right, that uses that password, and there are very sophisticated password cracking tools that do exactly that. And so we'll explore that later. But anyway, so there are better ways to use hash functions, but they're used in all sorts of important ways. Hash functions are kind of the basic integrity, one of the most basic integrity checking building blocks of crypto. The other main symmetric key building block that's very common is what we call a message authentication code, or MAC. And this is unlike a hash is usually, a basic hash doesn't have a key input. It just takes a piece of information, public, and produces a pseudo-random output. A MAC does take a key. It takes a document, something, and a key that's supposed to be shared by only these two parties that are communicating. And one way to construct a MAC, a common way to construct a MAC, is using a hash function. So, the naive way to do that is just to run the document and the key concatenated together, more or less, through the hash function. That's not the best way, but as a starting point, it kind of works. And then you take the output of the hash as the message authentication code. You send that MAC together with the encrypted message, for example, or unencrypted message across. And then the receiver is going to use the message and the secret key to recompute the MAC, or recompute the hash against the received message, and check to make sure that the received MAC is identical to the hashed output. Now, if only the sender and the receiver, only those two parties know that key, then anybody else, any attacker, Eve, who's trying to forge a different message or flip any bit in that message, will change what the MAC should be in a way that the attacker can't forge. The attacker won't be able to find a valid MAC that the receiver will reconstruct using that key, because the attacker doesn't know that key, and the attacker can't re-engineer the key because of the one-wayness of the hash function, right? So that protects the integrity in this scenario, in this simple scenario, provided the key is known only to those two parties, right? So this is an extremely important common use of hash functions. It's used all over the place. But again, like all crypto primitives, it's not perfect. There are ways it can be misused. Can anybody suggest something that might go wrong using a MAC if you use it in the wrong way, in the wrong context? For example, let's say there are three parties that are communicating, and the three parties share the same key. Alice is sending a message to Bob, but Charlie also has a copy of the key because it's a group discussion. What can go wrong?
Like anyone who has the key can actually force the messages. So.
Bingo! Yeah. So if more than two people have copies of that MAC key, then any member of the group can forge a member, making it look like it came from any other member of the group, right? So MACs are only strong authentication in the pairwise only two people know this key context. They are not secure in, a group communication context. You can solve that by having every pair of the group have a separate shared key, things like that. You can still use MACs, but you don't just distribute the key to all the group members. That will not give you a secure kind of group-wise authentication protocol. Make sense? Okay, so another, so we basically been talking about keyed hash message authentication. Well, you can use an unkeyed hash to create a MAX. There are also keyed hash functions that are designed to have a separate key input. And sometimes that gives benefits that we don't need to get into the details of. But basically, in general, we want kind of a cryptographic abstraction for a keyed hash function that takes a separate key and a message and produces a message authentication code that depends on both the key and the message. One very common construction for this is called HMAC, and this is a generic way to take a hash function and produce a keyed message authenticator. And because it just takes an arbitrary hash function, you can use HMAC to create a keyed message authenticator from any hash function, such as SHA-1, SHA-256, and so on. So these are called HMAC SHA-256, for example, right? And this, for technical reasons, we don't need to get into. This actually uses the hash function basically twice internally. It first hashes the key and the message. First hashes the key and the message, and then hashes the result of that with the key again. And this provides a number of security advantages. So internally, but just think of it as a black box in general for now. So basically, the upshot of all this is, we gradually learned the lesson that, ensuring data integrity is in general extremely critical, and a lot of people were forgetting to do it. Like, we only care about encryption. What can an attacker do against this encrypted data? They can't see it, so what can they do about it? Well, this turned into a big trap that a lot of, unsophisticated, developers who weren't familiar with cryptography were falling into, underestimating the importance of, the authentication part of communication. And as a result, this led to a consensus, a fairly broad consensus, that for most uses of encryption, it would probably be better to wrap up the encryption part and the authentication part together into kind of joint authenticated encryption algorithms, as an abstraction that does both of these things in a fashion that's evaluated and believed to be secure together. And so this authenticated encryption abstraction has become more and more popular. Now, there are plenty of ways to construct authenticated encryption schemes from normal existing building blocks. There are basically three very standard approaches to just combining any MAC and an encryption. You can either, and it basically amounts to the order in which you do the operation, either MAC then encrypt, encrypt then MAC. So MAC, then do a MAC on the plain text and then encrypt that, or do encrypt, produce a ciphertext, do the MAC on the ciphertext, or encrypt the plain text. So that was the third one. Choice B is encrypt the plain text to produce a ciphertext, in parallel MAC the plain text, and then send both the ciphertext and the MAC of the plain text. And so, basically three different constructions. And all of them can be secure depending on the context, but in certain other contexts, some of those can get broken. And so And so there's some security practices that have been gradually learned in terms of which tend to be most robust in what types of system examples. But because of the kind of the trickiness and the sometimes the bad ways these were sometimes used, more and more emphasis has been put on building authenticated encryption algorithms that are kind of an abstraction by themselves that basically take a common form of this these days is what's called authenticated encryption with additional data. And this is often used for encrypting messages or packets and with authentication. The basic idea here is an AEAD scheme takes a key as usual, takes a message A, takes two additional data A and a message M to be encrypted, produces a ciphertext C of the message, and a T, which is the authentication tag, right? And the nonce coming in the bottom distinguishes different messages because some of these AEID schemes are like stream ciphers in that they, they have to have that nonce. They become completely insecure if you don't use the different nonces for each message. So that's still a caveat in many of these schemes. But the idea here is the message gets encrypted to the ciphertext. The additional data A does not get encrypted. Usually you just send that data as plain text. And that, but the tag, the MAC tag T, depends on both the message data and the additional data A, the unencrypted data A, to ensure that you can authenticate even parts of the message that you're not encrypting for whatever reason. And in many uses, there's part of a message you can't encrypt because it's header stuff that the receiver needs to be able to read before it knows how to decrypt the message, right? So an example is IPsec routing. So there's typically a packet sequence number and other stuff that has to be added to the packet, and in the receive logic, the receiver needs to see the clear text of the sequence number and certain other little bits of metadata before it can actually do the decryption. It needs that in order to do the decryption, and so that gets transmitted in the A part. But then the AEAD scheme ensures that even though the A part can't be encrypted, it still at least gets authenticated. So if the attacker changes the A part, the T will change in a way that the attacker can't forge. Okay? And so, so these are illustrations of some of the common ways to create authenticated encryption ciphers, AEADs. We don't need to get into the details. And there's many other constructions. For example, one of the very common ways and one of the most efficient and very popular ways of doing this is a scheme called GCM, Galois counter mode. It's not totally trivial. I won't get into the details, but it uses a block cipher as the primitive. It uses a block cipher in various ways to get both encryption and authentication in a way that's both quite efficient and very parallelizable. So that's the main benefit of this scheme. Most of these encryption, the uses of the block cipher can be fully parallelized, and so that's so it's similar to counter mode, but with an authentication added. So that's why that's popular. Okay, so that's the summary of the key, the important symmetric key encryption and authentication stuff we're going to talk about. So let's take a little break for 15 minutes and come back at 5:30. Okay.